Hello everyone, let us start today lecture about pulse transfer function. So we will start today with pulse transfer function. Pulse transfer function. Transfer function, and let us look for the inverse Laplace, inverse Z transform, inverse Z transform. Z transform which will be utilized to convert the discrete transfer function from complex into the sequence domain. Therefore, we are going to look into examples where we use the transfer function, and later on when we use inverse Z transform to obtain the solution to the difference equation. So if we consider just a simple example of the tank system that has the following state space representation. K plus 1 x k plus 1 is equal to x of k x of k plus 3 u of k and output of the system is given as 5 equals k 5x of k and we have a certain initial condition if x0 is, let's say, some given height of the tank. We're interested in what is the transfer function first of this system and how to find response. Response to the step input program. On the step input. So this is the standard thing that we usually have in the linear system theory, that we have a model that is step function so step function that is described by some difference equation that we obtain just from obtaining the discrete representation of some continuous representation. And now we are interested in this discrete world. How do we obtain and how we calculate first transfer function and we find response. Therefore, as we're taking Laplace transform in the continuous domain, we take a Z transform. So we do Z x k plus 1 equals to Z transform of x of k plus 3 same z transform of u of t. Okay. And we already know that if we take z transform of this expression, we obtain the d multiplies x of k minus d x of 0, which is nothing but this term here, and here this is 2x of d now plus 3 u of d. After we shift this to the left side and we place this on the right side, we can find expression that says that x d is z divided by z minus 2 multiplies x is 0 plus 3 plus 3, and this is again z minus 2 u of z. Okay, so we have a system response. Of course, we also know that y of z is equal C matrix multiplies x of z. In this case, it's 5 multiplies x of z. So we will not pay attention right now on the output, but we just want to put this notion here that this is the initial condition contribution. Initial contribution, and this is the input contribution in the response of the system. Contribute in the response. So we have these two things, and now interesting thing would be once we found the transfer function, so in this case we can look that this is the transfer function here that relates input to the state, and here we have a transfer function that relates initial condition to the state. So we have these two contributions, and therefore we want to look what is the step response in the case of having these two contributions. So let us just work out this, because this is easy. This part, the initial condition contribution, is quite easy, and I will write here that this entire part, just write y of z equal 5 multiplies 5 is given here, as you can see in the previous equation. 5 multiplies z divided by z minus 2 x 0 plus 5 multiplies 3 z minus 2. But we know here that if we have a step input, the z transform of the step input was z transform of the unit step. It was, we denoted as a u of t In the previous, here it was just z minus 1. Okay. Therefore, we have here that entire expression in complex variable z becomes as follows. Now we have to work this part, and we have to work out this part to shift it back to the difference equation, such that we understand at each time instances this y, or how y of k behaves, because we don't know y of z. Y of z does not tell us about really what is happening. Now, when we look at this expression here, we notice that z minus 2 is nothing but the z transform of the geometric sequence 2 of f. Alright? Because remember, it was z transform a of n, and we already demonstrated that that was z minus a. So whenever you see this structure, z minus a, you already know that this is the sequence. Once you take z transform of this sequence, you get to this expression. In other words, we already know that this term is going to be 5 multiplies 2 and x is 0 in the difference world. What happens with this term next to it? We will work it out, and there are two ways to solve this term to the left, and I will emphasize this. One is to use power series method. And another one is use the partial fraction expansion, similar what we had for the continuous domain. Number 2 is partial fraction. Partial fractions. So let us quickly demonstrate this. And how we are going to do. First, let us do partial fraction expansion here. We just look at this form here, and I'm just going to rewrite this term here as I as y of z. Let's say this is prime. This prime doesn't mean anything, it's just I want to denote this term. Here as 5 multiplies 3, and here we have a z divided by z minus 2, and here we have a z minus 1. Okay. So now expression, whenever we have expression in this form, we put this in the following form. So we put the z here, and now we work, let's say this is now 15, and now we have a structure that looks like following: 1 by z minus 2 and z minus 1. Therefore, this becomes equal, and we can express these polynomial as a z minus 2 plus b z minus 1. Okay. And we can find out by equating the right side of this expression with the right side of this expression, what are the coefficients a and b, which finally leads that y prime, okay, this is the same procedure that we have when we have a Laplace transform instead of z we have s for the Laplace when we were finding the coefficients, and now we have a z, so it's analog to the lecture that we have in 4.6. And here we have that we will have a 5 multiplies 3 is essentially going to yield 2k minus 1. How do we know that? Because these two factors are going to be 2k, essentially sequence is going to produce, and this is already factored as z minus 1, because when we put this z on the other side, we will obtain that this is the same like 5 multiplies 3 multiplies z. Z minus 2 minus 3 z minus 1. Okay, so therefore when we determine a and b, which in this case 1 and minus 1, we will have that here this z is coming from shifting back this into the expression, and therefore we can find out that y of k is now 5 multiplied 3, 2k minus 1. So this is the contribution that is coming from the term that is input driven. Overall expression becomes now y is from the previous part here 5 multiplies 2n or k, so y of k, we will call it y of k here, 5 multiplied 2k, x is 0 plus 15 multiplies 2k minus 1. Okay, this is now response of the system to the step input and to the given initial condition. So this is initial condition contribution, and this is response of the system due to the step input.